My name is David Meyer. I'm a relatively new PM here at DARPA MTO. I come from NRL and have a background in wide bandgap semiconductor materials like gallium nitride and its use in RF applications. Now, coming to DARPA, really looking forward to broadening my horizons and trying to learn new areas. One of the really interesting questions that I've been thinking about recently is, can we as a community do a better job of electronic system design and manufacturing? And so I'll talk about that today. So microelectronics advanced packaging. So this is basically a linchpin going from a core semiconductor technology and getting it in the right form to be able to be integrated into next generation systems and platforms that the Department of Defense is interested in. Now, for decades, MTO has spent a lot of effort in developing those core semiconductor technologies and microsystem technologies that enable improved performance at the system level. However, I'd say more recently, the office has been thinking about advanced packaging and what could be done there to improve functionality. And so, the best example of this is the flagship program, Next Generation Microelectronics Manufacturing, or NGMM, which is run by Michael Holmes, and you'll hear more about that tomorrow. But that's focused on this sort of first level of advanced packaging, where you're taking one or more chips or technologies and doing some type of 3D heterogeneous integration together and getting that into sort of that first level. But beyond that, something that I've been scratching my head about is in the second and third level of advanced packaging, which is broadly the board level and then the circuit card assembly level. These are relatively old technologies. The printed circuit board was made in the 1930s. This is hasn't changed all that much since its inception. And so I think it really begs the question, are there opportunities for improvement in that technology space? And so the bullets on the bottom of my slide here will be the topics that I'll cover in the talk today. They can largely break down into sort of software first, and then we'll talk about hardware towards the end. But I think there's an opportunity to really change the design process and do a better job of thinking more holistically about electronic system design. And so love to be able to do co-design of electrical, thermal, and mechanical considerations. Like to implement potentially new design methodologies, like inverse design methodology. I'll talk a little bit about what that actually is in a few slides. And then, reduction or better utilization of space. If you look at a printed circuit board or a module, there's usually gaps between discrete components and boards. What if the designer actually had access to those spaces and could use those to make more intricate cooling manifolds or power distribution or antenna technology? And so, thinking about it from a purely 3D standpoint, not a 2.5D, but a true 3D flexibility, enabled to the designer, what could they do with that? And then lastly, the hardware side of it, what could we leverage in terms of advanced manufacturing, in particular multi-material additive manufacturing processes that could help us to move from a discrete component assembly type of manufacturing process, where you're soldering components onto boards, to actually directly synthesizing the entire electronic assembly in one step using multi-material additive manufacturing. So we'll talk about that towards the end of the talk. So first, let's start out on the software side of things. And system designer, electronic system designer today really wants to understand multiple domains of a given design. You're going to want to have access to CAD tools to kind of define the form factor and the structural attributes of the system. You'd love to have the ability to do multi-physics, high-fidelity multi-physics simulation in order to understand the thermal crosstalk, the structural strain, considerations, and then the electromagnetic interference attributes of a design. And then, of course, you need to have the EDA component to do the electrical circuit design, topology, the layout, timing simulation, power distribution, et cetera, all of those fundamental aspects to an electronic system. And I guess I would make the case that there is plenty of software tools out there today that do a great job of doing this in those different domains, but there's not necessarily an integrated design tool that will allow you to, a single engineer or designer, to be able to have eyes on all those different domains at the same time. And so, I think there's been some calls for, bringing more high fidelity to the understanding of the multiphysics in EDA design. The quote there from EE Times kind of illustrates that. But I was actually looking at EE Times this morning, and the headline is "Simulation is now driving product design, not just validating it." So it's a very serendipitous timing of this. But this represents an opportunity to rethink these software products and leverage new types of algorithms and all of the wave of software and new types of computational and representation of physics in advanced design tools. So I'm really interested in hearing about ideas for how we can do that better. So in addition to the software tools, while we're sort of examining this from a holistic standpoint, I think it's worth thinking about the design methodology that's currently used for electronic system design. Typically, you'll have an emerging core technology, new semiconductor or new process node that is suspected to have system-level benefits in the final end system. And the way that technology makes it into the system is you start with the integrated circuit design. You sort of produce the core chip, then you put it in a package, and then you put it in a board, and then you put it in a module, and it's kind of in this linear sequential fashion going from the inside out of the bullseye chart shown on the slide. Now, this, I think the problem with this, and I've observed this in instances with specific design spins on products for the Department of Defense, the problem is that if issues arise at a later stage of this process, say when you're getting to the module assembly, it's very rare that a team wants to address that problem back at the origin, say back at the chip scale, right? That would introduce a lot of delay and revalidation of all the steps that led up to that point. And so typically my observation has been that teams will just engineer around it, and this is where good enough is the enemy of perfect. But what if it is we want higher performance, and what if the designer could address these problems at a different range or a different dynamic range of this system design, hopefully at the onset of this process. So one possible solution to this problem would be to adopt a different design methodology. Inverse design is a technique that has been used in the photonic integrated circuit community, and it represents the design methodology where a designer will have a region of their photonic integrated circuit where they will have a desired transfer function in mind. They can define their inputs, they can define their target outputs, but then they go and let a machine algorithm do an evolutionary optimization of the layout itself to produce that desired transfer function. And when you look at these things that are produced, they're very non-intuitive. They're non-Cartesian or Manhattan. They're very organic looking, and so I think that's really neat and exciting for that one application. But what if we could generalize that to all of system design and really allow for the formation of human-machine collaboration to produce much more intricate designs, complex designs that have higher performance, and we have a better understanding of the physics involved with them in order to predict their ultimate performance after manufacturing. So let's switch gears a little bit, and now if we talk about hardware. Now if we have this fancy new software tool and this new methodology, and we can make these really intricate 3D designed systems that have 3D freeform electronics and integrated cooling manifolds and antennas, et cetera, the next step is probably want to make it, right? So how can we do that? I think it's not a far stretch to imagine that if you allow for 3D flexibility, that you probably will very quickly get to designs that are not manufacturable using conventional methods. And so on the hardware side of things, we should think about, okay, how can we leverage new manufacturing techniques? And one example that I'm sure you're all aware of is additive manufacturing or 3D printing. What if instead of just, again, soldering components into PC boards, we could actually just synthesize the entire thing with an additive manufacturing capability? Well, if you take a look at a standard PC board and do a materials teardown on it, you see that it's made up of approximately 40 different materials based across 5 or 6 different material classes. So, the ability to deposit all those materials in one additive tool does not exist today, and this is sort of consistent with what Mike Sangelo was just saying, that the future really needs to start thinking about how do we increase that catalog of available materials together. And so it begs the question, okay, well, why is there not an additive manufacturing capability that has more options in terms of materials? One of the answers, or one of the challenges that emerges is that different types of materials like to be deposited at different temperatures in order to achieve bulk-like performance out of them. So what you're seeing up here on this slide is the typical deposition temperature range for several different classes of materials. And as you can see, it's kind of all over the place. This, I think, points out why you can't combine certain kinds of materials together, like, say, polymers and ceramics. If you were trying to print a voxel of a polymer material and then followed up with a ceramic a voxel that you put right on top of it, the sintering temperature for ceramics can go up to 2,000 degrees C. The polymers aren't going to be able to withstand that type of temperature processing. So this is a huge challenge, and I think at DARPA we like to look at challenges as opportunities to find new ways to get around this. So how can we get around these limitations instead of using temperature as the main method of delivering energy to do a certain type of deposition? What other techniques could we use? Up here I have 2 examples of sort of emerging techniques that I think are really interesting to think about. On the left, you have electrochemical additive manufacturing, and this is a technique that's being looked at by Fabricate Labs out of San Diego, small startup. And you can think of that technique as being sort of selective area electroplating, and they have a tool that allows it to be changed through the course of a build, and they can produce these really intricate 3D structures that have bulk-like properties, or basically the same type of properties that you could get out of an electroplating type of deposition approach, but in this 3D designed intricate geometry. So that's one technique where they're using electrochemistry instead of temperature to drive that reaction. The other one on the right from Formlabs is inverted stereolithography, where they're using photon energy or light to do conversion of a resin bath to produce polymers in a large area format. Another aspect of these is that both techniques are looking at a parallelization of their approach and moving away from the traditional 3D printer, single point source rastering type of way to produce these materials. Both of these I like from the standpoint of they're not using temperatures, that energy knob, but again, both of these are really focused on one single class of materials. And so what I'm really interested in, I'd love to hear from anyone who has ideas on this front, is ways to bring these multiple classes of materials together in a single tool to really expand that catalog of available materials that's available to the designer. And I think that'll be really exciting, not only for electronic systems, but for all types of different industries if we can realize that vision. So thank you very much for your attention. I look forward to talking to you in the future.